Good afternoon, everybody. My name is Patrick Greer. I'm a senior in the Ocean Engineering program here at USM, and today I'm going to be presenting to you my senior project, which was a mechanical system to measure the efficiency of wave energy converters. So first off, going over the motivation behind this project and kind of why I chose it. I've always been kind of interested in renewable energy and wave energy ever since I was really introduced to it. I think it was my first semester here we kind of learned about it. And as you may know, it's becoming an increasingly more important topic in the world. And if you don't know, wave energy basically harnesses the power of ocean waves to generate electricity. And it's actually the largest unused renewable energy source. And just another fun fact is that wave energy off the US coast actually have the potential to generate 64% of the country's total electricity generation. So on the top right here, we have a map of the wave power across the world. It shows the different levels. And then on the bottom right are some examples of different renewable ocean energy devices. There are many different types. Some may target the heave motion of waves. Some might target the pitch or the roll. So my original project was actually different from what it is now. Originally, I was going to target this type of converter, which is a oscillating water column buoy. And basically the way that this works is that it has a hollow chamber inside of it where water fills into it, and as the waves pass by it, the water oscillates up and down inside of the chamber and then pushes the air up towards the turbine, spinning the turbine and therefore generating electricity. So the first step that my plan was in making a buoy was scaling down an existing buoy. This is one that I found. It's actually from Portugal, and it's already a 1/16 scale down model. And the full dimensions are actually with an outer diameter of 30 meters and a length of 50 meters. So this is a very large device. And I came up with a scaled down dimensions with a ratio of 1:195. This is taking into consideration the time and cost and it actually being achievable. But the dimensions came out to be an outer diameter of 6 inches and an inner diameter of 3 inches and a length of 8 inches. So the first step in kind of tackling this project was to figure out if I needed to target a deep water wave or shallow water wave. And to kind of explain the difference between the two and the characteristics, first off, for the deep water wave, the depth needs to be greater than or equal to the wavelength divided by 2. And these have circular shaped orbital velocity. And if you look at the diagram, you can kind of see there's actually no wave motion because it dissipates at the depth where it's half of the wavelength. So there's no wave motion below that. And in terms of the shallow water wave, the depth needs to be less than or equal to the wavelength divided by 20. And these have oval-shaped orbital velocity, and the motion does not dissipate. It actually continues all the way down to the sea bottom. And ultimately, my decision to target a deep water wave stemmed back to the offshore deep water applications of these buoys. This is due to a couple of different factors. First off, the size, because of how actually huge these devices are. Also tourists. I don't know about you, but if I was on vacation somewhere at a beach, I wouldn't want to look out and see a buoy. So that takes care of that by putting them offshore. And also navigation of ships in and out of ports. That solves that problem by putting them offshore. So this is where my project kind of took a turning point, and I came to the conclusion that that was not achievable due to a couple of different factors. First and foremost is that the time and money limit, that played a big part. And also, if I was to create a buoy, I would need a way to test it, which would require me to also make a wave tank, a wave generator, along with the wind turbine generator and the buoy itself. On the bottom right is just an example of a wave tank and wave generator. And like I said, we don't have access to one of these right now, but thanks to our classmate, Marthinette, we're actually one step closer to that. But my decision was to tackle the first step into creating a wave energy converting buoy, which was to create a system to conduct testing in a controlled environment. So explaining more about my new project was that the goal was to mimic a deep water wave mechanically in a controlled environment. And with this, you're able to test the efficiency by comparing the output voltage from the turbine to the expected energy from the wave characteristics that you can calculate. And how you would do that, you would start off with the formula for wave energy, with the water density, gravity, and wave height. And then from that, you're able to calculate the wave power. And then from the power, you're able to calculate the voltage. So you would compare this voltage to the actual voltage that you're reading out of the turbine to then determine the actual efficiency of it. And the next step was figuring out the exact wave dimensions to target. So like I said, the depth needs to be greater than the wavelength divided by 2 for it to be considered a deep water wave. And the buoy length that I came up with is 8 inches. So I came up with a depth of about 14 inches. This therefore would make the wavelength need to be 28 inches. And another criteria to note is that if the wave height over wavelength exceeds 1/7, the wave will break. So with that in mind, I tried to maximize that ratio to 1/6, which would make the wave height have a value of 4.5 inches. And obviously this isn't 100% realistic, but it is possible. And the reason for maximizing it like that is to maximize the airspeed actually coming out of the chamber and maximize my chance of actually spinning the turbine. But from all of that, you're also able to calculate the wave celerity and the wave period, which came out to 0.7 seconds. And here's just a list of all the different components in my project. Starting off with the wooden brace, this basically holds everything together. There's a reciprocating linear actuator, which actually has an adjustable stroke from about 1 inch to 6 inches. But for my project, it's set to 4.5 due to my calculations in the previous slide. And it also has an adjustable speed, so you can change the wave period, basically. That's connected to the piston though, acting as the water surface, oscillating up and down within the acrylic tube, which is acting as the buoy structure that is braced by these braces on top and below of the tube. There's also an optical sensor right here at number 6 with a mount for that. I'll go more into detail about that later, but then you have the wind turbine generator at the top with the mount for that. And I also created a protective arm cover for the linear actuator. And the microcontroller is actually inside of this breadboard housing where all the wires go and everything. And the OLED display is up here on the top right. You can't see it because this is a CAD model right here, but it is on my actual product. So like I said, this is a CAD model that I created in Fusion 360, and everything that you see that's white, I 3D printed using our 3D printers here in the lab. So now I'm going to go into kind of each component and explain further in detail. So first with the turbine, this was the turbine that I actually ended up using for my project. And there's a little bit of worry about if it was going to work or not. So I started out by testing it to figure out what speed I need the air to be to actually spin it. So I tested it by holding it out the window of my car, and readings were made at different speeds. And the graph on the left shows the results from that. The turbine would always start spinning at about 10 miles per hour, and the voltage would increase from there. So with that idea of the airspeed that I need, I was able to calculate the area that I would need for the hole right here at the top opening to be by using the continuity equation, which basically relates the surface area and velocity at the two different ends of the chamber. But with that, I was able to calculate the size of the hole that I needed to make, which came out to roughly 1/4 of an inch squared. So once I had all of that set up and the turbine mounted above the opening, I then began testing it. I started off with an oscilloscope to test the AC output voltage. And the reason for using this first was because the microcontroller can actually only handle so much voltage. So this was an idea. The purpose of it was to get an idea of the magnitude and frequency of the voltage that I'm actually dealing with. So after that, I was able to set up a voltage divider so it could drop the voltage to a reasonable range that the microcontroller can handle. And after I did that, I was able to sample the voltage at a frequency of 1 kilohertz with the microcontroller. And on the right is the results from that. You can see that it's basically an exact replica of the actual wave that I'm creating, because as the wave reaches its peak, the voltage is also going to reach its peak. Sorry. And it has basically the same period of 0.7 seconds. So now going into the optical sensor and explaining what exactly is it. It's a sensor that uses a light source to measure speed. And the light source can either be visible, infrared, or laser light that is either interrupted or reflected by a rotating object, and it's then read by the phototransistor. So looking at the diagram on the right, these are two different examples of them. The first is a slotted sensor where the LED is directly across from the phototransistor. And the way this one works is when an object rotates in front of the two, it interrupts that light being received by the phototransistor. And the phototransistor then causes the voltage to drop. And you can use that in your coding to basically count one full rotation of an object. And it's basically the same idea for the reflective sensor. The main difference is that the LED and the phototransistor are side by side, and instead the light is being reflected off of that object and then received by the phototransistor. And right here is a picture of the sensor that I actually used for my project. You can see on the left is the infrared LED, and then on the right is the phototransistor. And this has a sensing distance of up to one inch and a response time of 15 microseconds. Some of the advantages of using an optical sensor is that there's no direct contact needed. It's relatively high accuracy and easy detection. But also disadvantages of it can be that ambient light can interfere and it has limited range. Obviously 1 inch is not very far. So for the mounting for that sensor, I first made a CAD model in Fusion 360. Down at the bottom left, you can kind of see where the sensor slides into position with these 4 little slots. And then on the other side, it has these 2 openings for the LED and the phototransistor. And then on the right is the actual results after 3D printing it and mounting it on the wooden brace. Another thing to note is that I glued a small piece of paper on the linear actuator so that basically it would have a flat surface to sense when it makes one full rotation. Another aspect of my project was reducing friction on the piston. So originally, I just 3D printed it like on the left. And very soon I found out that this was a problem because it wasn't sliding smoothly within the tube and squeaking a lot. So tried to fix that by 3D printing it with a smaller diameter, giving room to glue felt material all around the edge. If you don't know what felt is, it's basically like a wool material, like a cloth. Therefore, reducing the friction on the piston, and it allows it to slide a lot more smoothly within the tube. I also created a protective arm cover for the linear actuator. This actually has an ingress protection or IP rating of 2.0. And just to explain what exactly that means, the first number represents its protection against solids, and the second number represents its protection against water. And the number 2 basically means that it's effective against adult-sized fingers or objects greater than 12.5 millimeters. So it basically provides safety for the user to not possibly get their fingers stuck or anything like that while operating this system. But this is another CAD model of that and the 3D printed result. And so now to kind of explain how it all comes together and how it all works is, so you have the linear actuator, which oscillates the piston up and down. This represents the wave. Like I said, you can adjust the stroke of it to determine the wave height, and also you can adjust the speed to determine the wave period. And as it oscillates up and down, it drives the air through the top and spinning the turbine. That voltage goes into this housing, and it's then read by the microcontroller and displayed on this OLED. And this is a little part from my code. I don't want to bore you all with code, but to quickly explain kind of how it works, it will display this on the left for 5 seconds, showing the wave period with the optical sensor. And then it will display this on the right for 5 seconds, showing the peak voltage and the efficiency. One thing you might have noticed is how extremely low this efficiency is. And one thing to realize about that is that my project wasn't on creating an efficient buoy. It was actually a system to test it. But in terms of optimizing it, there are many different things that you could do. The biggest thing, in my opinion, is a bidirectional turbine, which allows the turbine to spin both directions. This is crucial because as the wave rises, obviously there's going to be air flowing out, but also as the wave falls, there's going to be air sucked back in, trying to spin the turbine in the opposite direction. That's why I say bidirectional. And also the placement of the turbine, currently mine is mounted above the opening when it really should be mounted within that opening, so there's no air just flowing out. Also, controlling the airflow in and out could be another aspect. You could optimize this. So for the results and conclusion, I was able to successfully create a mechanical system that can imitate deep water waves and test the efficiency of oscillating water column wave energy converting buoys. It displays the wave period, output voltage, and efficiency on the OLED display, all in real time. And it also has the potential to act as a testing platform for future projects in wave energy conversion. And looking back on my budget, everything was relatively cheap. Came out to a total of under $200, and we're actually provided with $250 from the program. So I was able to keep it under that. And also looking at the technical and soft skills that I learned and also utilized throughout the project. First, for the technical, I definitely gained a deeper understanding of wave energy conversion. I also gained a lot of experience in Fusion 360, C++ coding, and 3D printing. And I was also able to utilize circuit analysis and hardware integration. And lastly, data analysis and interpretation. For the soft skills, this could be a very long list, but this is kind of my top 5. For the first 2, decision making and problem solving, these are really important because you're basically in the driver's seat for this project. You make all the decisions yourself, and you have to be very smart in doing so. Also, organization. I think this is important because being organized in what you do kind of help with when looking back on your project and being able to build on each step that you take and the progress that you make. For patience, that's a really big one for me. I think being patient helps a lot. Just having an understanding that you're not always going to make the progress that you want or that you think that you need to, but just staying patient helps with that. And also just being confident that you're ultimately going to reach that goal that you have for yourself. And finally, for the surprising aspects, first, it had a lot more details than I expected. You have to have a reason for every little thing that you do or part that you use. And also, people are not lying when they say time flies, because this project definitely flew by for me. But that's about it. Thank you all, and I'm open for any questions.
Question. What was the most challenging part for you in this project?
I think it was probably when I came to the conclusion that that original project that I had wasn't achievable, and it took a little bit of time to figure out what I was going to do next, and that was probably the most stressful part, kind of figuring out what to change it to. But once I figured out what I was going to do, that kind of helped a lot.
What are you most happy about or proud of with this project?
I would say getting to see it all come together, just from an idea to everything put together, is kind of a really satisfying feeling. And yeah, I think that would be mine, honestly.
So, can you turn it on right now? Is it working?
Do you think you could put a switch in there so we don't have to?
Yeah, that would be a lot more convenient.
Be a nice little addition.
Sometimes kind of both of those. It's done this before, I don't know why.
There you go. You should turn off all of them.
What you doing it again?
Wiring on there?
See now.
Says 1.27 seconds right now.
I'm sorry?
1.2 seconds.
That's basically how it works.
So how did you calculate the wavelength?
So basically I used that ratio of 1:7 where it breaks. I tried to maximize my wave height by making it 1/6. So that's how I came up with 4.5 inches for that.
So, but, well, like you said, it would be great if the turbine was inside A2, so that it would be a direct, application of the continuity equation there. But, so from the speed of the piston or whatever you call it, that pushes the air up, if you consider that the air-water interface, can't you use that velocity to actually back calculate? Assuming that your period is the period of the waves, you can actually have this represents this period and this height for waves in an actual oscillating water column.
I'm confused what you're kind of getting at.
So in an actual oscillating water column device, the movement of the air-water interface is due to the wave
Yes, sir.
vertical motion, right? The heaving motion that you're targeting. So that's related to the vertical orbital wave velocity.
Yes, sir.
So meaning you can really relate this speed of your piston to an actual speed, vertical velocity of a wave, which is a function of wave height and wave period. And you know the period, you are reading the period right there. So you literally can also back calculate the corresponding wave height. So you can say, okay, my device is mimicking waves with this height and this period.
Yes, sir.
So that's why I asked. How did you calculate the wave height? But didn't get the answer.
I didn't take that approach, but I understand what you're saying. You can do it that way.
Well, I mean, he used the maximum allowable wave height. Before the wave started. That's why he is more or less to jump at the period.
Yeah, but he's adjusting the speed of the piston. That means that the adjustment is happening. Wave height is changing. It's like different waves.
Well, the wave height stays the same, but the maximum frequency, the wave height adjustment. Period is slowly. Period changing when the wave height is. So at the period of what's the maximum period? The 1.8 seconds, or 1.7 seconds. That's where the wave would be so short that it does particular stroke.
Oh, okay. So it's for a constant wave.
Adjusting the wave height is difficult because we can only cover period.
I see. Now could be vice versa. Could be considered a constant period but changing wave.
Period change. Each strength, hold up, period change.
Sure. Assuming wave height is constant, but it's the same thing. The velocity, the function of velocity is pi times h over wave height over wave period ratio. You are assuming that your wave height is constant, so as you change your piston, well, the period of the piston, you're saying that reflects a change in wave period, but it could be considered the other way around as well. Because as the wave height is changing, the vertical orbital velocity of the wave is going to change in an oscillating water column device. That means the air-water interface will go faster or slower.
Sure.
For constant period waves with different wave heights. That's what I'm saying.
Yeah, but he just can't adjust the wave height completely. He can adjust the period and the velocity, vertical velocity.
Normally, is that he has to change the play with the actuator.
Yeah, you would actually be able to see, but it's underneath this. It's like it slides to a different length, so you can adjust it.
Velocity and period change together. Flow change.
And what was the reason behind the turbine not within the enclosure?
Because it's actually larger than the size of the opening that I came up with. So I just placed it above it because obviously it wouldn't fit.
So how much of your loss in efficiency may be attributed to the fact that it's not in the enclosure?
I think that's a large portion of it.
Quite a good deal.
So I have always a take on it. If it would really be the enclosure, the air in the reverse direction.
Yeah, that's also.
So now we have to go to 3 on the other and so
Oh, it's shielded.
you would have to put belts in it for that. There's room for another year or two.
The rest. I think that's the biggest accomplishment, actually.
Yeah, I think it's great.
Yeah, anybody else? No more questions? Well, then let's give Patrick a hand. Very good.